In this video, we will explore C++ priority queues, an efficient data structure that allows elements to be processed based on their priority. We'll be focusing on how to use priority queues effectively using the standard template library, also known as STL. Let's define what a priority queue is. Unlike regular queues where elements are processed in first-in, first-out order, priority queues process elements based on their priority. The element with the highest priority is always at the front and gets processed first. Under the hood, priority queues are typically implemented using a heap data structure, which ensures that the highest priority element can be accessed quickly. The C++ standard template library provides a built-in implementation of priority queues, making it easy to use this data structure in your programs. Priority queues are efficient and useful for tasks where processing order matters. To use a priority queue, include the queue header. Then you can declare a priority queue of integers. You can insert elements using the push method. To access the element with the highest priority, use the top method, which will return the value 4 in this example. Priority queues support several common operations, each with its own time complexity. The push operation, which adds an element to the queue, has a time complexity of big O log n, where n is the number of elements in the queue. Similarly, the pop operation, which removes the highest priority element, also has a time complexity of big O log n. The top operation, which retrieves the highest priority element without removing it, has a time complexity of big O1, meaning it's very fast. The empty operation checks if the queue is empty and has a time complexity of big O1. Lastly, the size operation returns the number of elements in the queue, also with a time complexity of big O1. Here's an example of how to use these operations. First, include the necessary headers, queue and IOStream. Inside the main function, declare a priority queue of integers. Then, push some elements onto the queue such as 10, 30, and 20. Next, use a while loop to iterate while the queue is not empty. Inside the loop, print the top element and then pop it from the queue. The output will be 30, 20, and 10, demonstrating that the elements are processed in descending order. By default, standard : priority queue uses standard : less as the comparison function, creating a max heap where the largest element has the highest priority. However, you can customize the priority order by using custom comparators. For example, you can create a minute heap where the smallest element has the highest priority by using standard : greater. You can also define your own comparison logic for complex types. The third template parameter of standard : priority queue controls the comparison behavior. Here's an example of how to create a minute heap. Include the queue and IOStream headers. Inside the main function, declare a priority queue of integers using standard : greater to create a minute heap. Then push some elements onto the queue such as 10, 30, and 20. Now, the smallest element will be at the top. The output will be 10, 20, and 30, demonstrating that the elements are processed in ascending order. You can also use custom types with priority queues by defining a custom comparison operator. This allows you to prioritize elements based on specific attributes of your custom type. Here's an example of how to use a custom struct with a priority queue. First, include the necessary headers, queue, IOStream, and string. Then define a struct called task with a string name and an integer priority. To customize the comparison, overload the less than operator. Inside the operator, compare the priorities of the two tasks. Now you can create a priority queue of tasks. When you push tasks onto the queue, they will be prioritized based on their priority value. The highest priority task will be at the top of the queue. Lambda functions offer a flexible way to define custom comparators for priority queues. They can be defined inline without modifying your types, which is useful for temporary comparison logic. Lambda functions can also capture variables from the surrounding scope, making them highly adaptable. They work seamlessly with any container adapter, providing a consistent way to customize comparison behavior. Here's how to use a Lambda function as a comparator. Include the queue, vector, and string headers. Define a struct called person with a string name and an integer age. Now, create a Lambda function called CMP that compares two people based on their age. The youngest person will have the highest priority. Finally, declare a priority queue of people, passing the CMP Lambda function as the comparator. This will create a priority queue where people are prioritized by age. Priority queues are used in various practical applications due to their ability to efficiently manage elements based on priority. They are commonly used in task scheduling systems to prioritize tasks based on importance. Dijkstra's shortest path algorithm uses priority queues to find the shortest path between nodes in a graph. Huffman coding for compression uses priority queues to build an efficient coding tree. Priority queues are also used in event-driven simulations to process events in the correct order, and in CPU job scheduling to prioritize processes. Lastly, network packet routing uses priority queues to manage the flow of data packets. Here's an example of how to use a priority queue in a task scheduler. First, include the queue and string headers. Define a struct called task with a string name, an integer priority, and an integer duration. Then, create a function called process_task_queue. Inside the function, define a Lambda function called CMP that compares two tasks based on their priority. Create a priority queue of tasks, passing the CMP Lambda function as the comparator. This will create a priority queue where tasks are prioritized by their priority value. To optimize the performance of priority queues, consider these tips. If you know the number of elements in advance, reserve capacity to avoid reallocations. Use the in-place method instead of push when possible, as it can be more efficient by constructing the element directly in the queue. For large queues, consider using custom allocators to manage memory. Avoid unnecessary copying of large objects by using references in your comparison functions. Here's how to apply these tips. Include the queue, vector, and string headers. Inside the main function, prepare the underlying container by creating a vector of integers. Then, reserve space for 1000 elements to pre-allocate the memory. Next, create a priority queue with the existing vector. Finally, use in-place instead of push to add elements more efficiently. In summary, C++ priority queues are container adapters based on a heap structure. Elements are processed based on their priority, not their order of insertion. By default, they function as a max heap where the largest element is processed first. Insertion and removal operations have a time complexity of big O log n, while accessing the highest priority element has a time complexity of big O1. For advanced usage, you can use custom comparators for specialized ordering and Lambda functions for flexible comparison. They work with custom types and structures and are efficient for priority-based algorithms. They are ideal for scheduling and optimization tasks. Priority queues provide a solution for problems requiring priority-based processing. They combine the simplicity of queues with customizable ordering, making them an essential tool in the C++ programmer's toolkit. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.